Okay, I guess let's start. So, as always, we have a bottle of tea to keep us through the night. So we're going to go and see where this leads us. Okay. I still have issues with my my window switcher, my scene switcher. I really want to bring my browser for the streams inside Emacs, but I never managed to get a version of this working fine. In consequence, I still have two windows, this one and that one. Here we can see the project, though I'm covering the thing a little. And we're going to do a few things in here soon. We're going to take it quite slow today. I wanted to prepare for this day, which was one of the motivation for doing my two first streams of the year in video game. However, I was kind of taken by other projects and I procrastinated until it was too late. So I'm very, very unprepared for this. The only thing that I've done is play with Ocaml LSP a little, which we're probably going to be using. Yes. So I don't even remember how you thing, how this project is supposed to be compiled. This is really ugly. Let me kill everything. So we can open a vterm. I didn't expect that. What? I'm very confused. What? Okay, this is really starting badly. I didn't test vterm before I set up, and I'm not sure how to debug this. Okay, give me a second. What? No. I'm I'm trying. I don't know what's happening. Has happened to another Nix user. No, I clicked the wrong button. Okay, this is starting absolutely delightfully. What can we do? So we have this. I need a terminal. Can I start NC term maybe? With bash. I guess that will work for today. We won't have. I'm gonna use this. I think. We're not in the wrong right branch because of course we aren't. I thought we master. Something's wrong. Wasn't it working exactly? Okay. Oh, I actually put in master. Okay. Well, that's one hell of a start. Okay. Let's see. Dune build. That's hilarious. Okay, let's have a look at I should have prepared a little. At the Circle CI Dune build. So we know it worked at some point. I don't have the right version of Dune for some reason. Which might be part of the problem. Oh, that's hilarious. Okay, Ocaml update. I have no idea. We might See, I didn't even try to build it apparently before I came here. Isn't that fantastic? What's happening? So let me see Ocaml upgrade. I did a few things, but I don't remember actually what last week. Oh dear. Look at this. Want to update everything. Does it want to update Dune? 2.7.1 to 1. Is this just because... Is it just because the Dune thing is wrong? Not Dune project. Maybe. Lang Dune. Maybe I just need to say 1.4 here. Didn't give me the warning this time, so that's probably better. I have no idea what's happening here. Source. Untitled. I don't even remember what this is. Haha. Okay. Okay, this is the best stream ever. 206. I could open. Oops. LSP. Okay. I know whom to complain about this. I guess it's pp_set or something. Ooh. It's also very elegant. I don't even know if I'm using the latest version of containers. Probably not. Maybe I should update. I also want to update the Ocaml version because there's a few stuff is happening in my status bar. Something is having fun with my computer. Okay, LWT using datalog configurator. Doesn't seem to be an update of containers though. Oh, like I know I installed something in my open switch before I got to that. I must say that I didn't like touch Ocaml since probably 2019. It's been a while. I have no explanation for what we are seeing. So I need to check. So let me switch to my browser, which is going to be annoying. GitHub CQ. I think that's the address. No, it isn't. Oh, I think it's for Ocaml containers. That's better. Okay. So we have the documentation here. Boom, boom, boom. Bigger. I don't have a clue which version I have. Let's just hope for the latest. I don't know. CC list. And we're looking for what? PP. That's gonna take a while. Maybe PP space works. Yeah, better. So that looks correct. That looks like it's the same thing. CC is a printer, except that it's unit printer, but I think it will be the same thing. Yeah, it's the one. Yeah. And a printer is a formatter to unit, and I just want to say it's a string. And so there might be a cc string.pp or something that would cc strings. No cc strings. I guess maybe it's just fprintf. No, kprintf. I don't know why something changed. It's like format.kprintf. That doesn't look correct. Let's check. Of type, this expression has type. That is brilliant. It doesn't happen all the time. Okay, this is going to be a bit hard. Doing build, please. Wow. Yeah, that's not the one. But we agree. That printer is still a format to unit. Oh, sorry, you didn't switch back. Thank you. I really like. I hate this situation where I need to switch in browser and stuff manually. So you didn't see, but the type error is nicely truncated. I just need to add a string. So maybe there's a, I think this is just simply a PP thing. General pretty printers thingy. No. Some stuff has changed the last time. Oh, there's a CC string. I'm just bloody blind it is. And so here I probably have a PP. It also takes the formatter as the first argument. That is a bit puzzling though. CC list, PP slash, ruby space, sorry. That returns a printer. Why is it different? Is there a printer thing here? Oh, I'm not in the, sorry. I'm looking in the browser. I'm trying to find the right way to do this and I'm already stuck and I have no idea. This is also the latest version of Ocaml. It uses these things and I want to use them, but I'm going to delay that until next time, I think, unless we really think it's a good use of all time. So I think that basically the answer is this is annoying. Fun format. Oh, I wrote KF printf. Maybe it's K printf. Oh, it's deprecated. Okay. So. Really? I'm gonna flip. Supposed to be unit arrow unit. Really? Okay, we managed to compile. Just took us 15 minutes. That's brilliant. Let me take a second. Okay. I poked someone for the next time. Okay, that's brilliant. I'll just port the entire project to the latest version of Ocaml later. Soon, I think. This is not even what we're interested in. So, now that we have something that works, that was the adventure of a lifetime. Wow. It might have been my most disastrously starting stream of all time. I apologize. Right. So one more thing, and I'm going to do a new file. datalog.ml. I'm going to explain why I'm coming back to this project first. So what are we doing? There's basically two steps, two parts to this. Part one is generalize the compilation engine, which takes description of a randomizer thing, or randomizer situation, yeah, randomizer's logic, as we used to call him, and returns a SAT problem whose models are valid valid shuffles, or okay, valid or logical shuffles. By which I mean that it follows a bunch of constraints that usually mean the game is completable within this rule set. That is specified in the logic. Okay. And want to generalize this to compile like general datalog programs without negation, which I don't really know what we could do with. Why? Well, that's because datalog is a fairly generic language, so it allows us to define more complex logic. It also cleans up a bit of the code which is very ad hoc. What can I say? It's just, you know, well, like not very very ad hoc to the details of the problem space, and might not generalize beyond the logic of LTTPR, which I know best. More LTTPR next week, by the way. I'm currently going through the increasingly evil Christmas special. I'm way beyond the curve there. And I've got nice ideas of how to do it. I'm going to show it in a minute. Oops. The other thing is I found a way to generate random approximately uniform models of type checkers. 2020. Sorry. Uniform models of type checkers. Not type checkers, of SAT problems. Or too many type checkers. Without relying on an expensive compilation step. I should say there's a trade-off here. Trade-off may be harder to debug because I don't really know how to output proofs. Also counting approximately the number of models. These two things are related. It's not swapped in right now in my mind, so I don't have the, like, I have the documentation somewhere. When we get to this, I'll dig it up and explain how it works. It's actually like fairly intuitive when explained, but fairly clever. And right now, I'm kind of forgetting. If I remember correctly, I need a counting mechanism to be able to generate a random model, which is interesting. Hey, David. Good morning to you too. It's almost time to wake up. The colors have changed. Maybe that's because it's slightly different. What colors do you mean exactly? The main advantage is that it's going to be much faster. Oh, am I on the, oh dear. I was typing all this, nobody was watching. Here, it's in my Emacs, thank you. No, the colors are back. Yeah, I have a problem with this scene switch. I need to do some adjustment, but I've been too lazy to look into my configuration the past couple of weeks. And I kind of forgot about this problem until I got back to it. But yeah, I couldn't be bothered. It's going to be much faster, so it's it will hopefully be quite imaginable to generate custom logics on the fly and draw from them. This can handle things like pre-filling the Gannon's tower, well, not just Gannon's tower, or multi-word logic. Of course, it's like if you compile, you get a very, very fast and accurate thing, but the compilation requires, like, it's very exponential. It was not clear. The compilation method was viable for a full logic anyway. Okay, so that's the general plan. I will have to switch back to my browser now, and I need to not forget to go back to Emacs, and I'm going back to Emacs. Why do I need to switch back to my browser? Because I want to show, I'm extremely well prepared tonight. I plan to be prepared, but family stuff is sometimes more important. Understand always. Okay, so here is a paper that is going to be extremely useful for us. Datalog game plan. Haha. What's my idea? So compile datalog to a relational. Oh yes. Thank you. I'm very good at forgetting it. Thank you. So compile datalog to a relational model. Right. So I want to pause and say something. There's a newish Emacs functionality called EAF, or Emacs Application Framework, that contains a web browser, which would be quite nice for these streams, because I could just pop the web browser in an Emacs window. And I can also use like plenty of Emacs3 in it, which is not really what I care about right now, but I would just have everything in a window. That would be quite a bit neater. But I never really understood what I needed to make it work, considering that I source my Emacs from Nix, which is usually good, except in that particular case, vterm broke, and I didn't realize I could use ANSI-term as a backup. I'm going to fix that during the weekend, probably. There are other ways, like running Emacs, and there's plenty of ways for me to have a browser in an Emacs window, but none that I have managed to make work yet. But one day, hopefully, we'll just never leave the Emacs session while we're doing programming, which will make things quite a bit easier. Meanwhile, so to a relational model, yeah, following, for instance, the method indentation of databases. At first, we're going to just compile things very naively, and maybe we'll revisit and do some optimization. Optimizations are cool. And then use the method in the cod paper. I'm going to just paste the link. This is fundamentally interesting, the way it does this. To compile the relational model to SAT, which is what they do, but for a slightly different version. So basically, we make it so that database instances of, in the sense that datalog, still doing this, I don't understand why, means it, aka facts, are the models of our SAT problem. And that's what we want to enumerate. So we're just solving a datalog problem to find all the instances, all the database instances that verify a certain constraint that we express as datalog. That like a goal is attainable. I think it will work. So it's using a datalog in a pretty curious way. That being said, interactions of datalog and SAT solvers have existed before, just not necessarily quite in that way. This seems to be related to program analysis in a way that I don't really understand. Okay, so other than this, what do we want to say? We want to say that so contrary to cod, we cannot use symmetry breaking formula. We do really want all the models, since at the very least we are counting them. However, I believe that symmetry breaking formulas or formulae, let's keep it pompous, I key to encode multiplicities. Having two of the same item, e.g. swords in LTTPR, of which there are 4. Another important thing is we can't model recursion inside SAT. However, we are going to make an assumption. There's a finite number of atoms. In database parlance, we would say that every column has a finite type. Okay, this means that we can actually bound the number of iteration and translate this into a static problem. Another thing also, code notes that because matrix composition or relation composition is associative, you can use so-called fast exponentiation to compute transitive closures. However, I don't think we have anything really. I think it should be here actually. Okay. Oops. Associative. So our iterations will be much more pedestrian. Okay. So how do we want to do this? I don't know how to approach this. So we kind of want both in the relational system and the datalog thing to be able to declare or base relations, the one that are part of the model. I should say, well, I'll get to that later. So how do we represent the simplest possible a prolog program? Let me see if I had an answer for my question earlier. So about our thing earlier, we can Still works. Let's check here. Fantastic. So a datalog. Datalog program consists of a collection of instance relations relation declarations with name and arity. I don't know why it does this. I think it just, yeah, it wants to add, but does it work in like I do meta queue? Oh no. So two different methods of filling do two different things, and that's a bit painful, and I don't know why that is. Spell check madness. Do you want me to clean the spec check a little? Accept buffer. The underline come from the spell checker. It's flight check. I have flight check configured as having as running inside comments in prog mode. You can look at my my Emacs configuration. It's online, by the way, now. github.com/aspivac/.files, and you can find /Emacs. Well, in the tree you'll find Emacs. A collection of instance declared declarations, I guess, with name and arity. I don't know why that was, but okay. A collection of rules defining whose heads are declared relations and right-hand sides are either are lists of instance relations and declared relations. That's a bit painful, ain't it? I don't know how to represent it in a way that is convenient in any way. A goal, which is a collection with variables and stuff. So not really the relation, it's of course. Okay, I'll figure out how to clean this later. A goal, which is a collection. This is absolutely hilarious. Which is a ground formula. Well, a ground conjunction of atoms built of instance relations and declared relations. A relation program will be much of the same, except yeah, we'll have unions, we'll have some operations on relations. We'll find a way to write this. So how do I want to go about this? We probably want names to be strings. An alias for the type of strings. Thank you. And so a declaration is an array colon int. Oh. Something like that sounds about right. You can do the prolog thing and say that a declaration is the name of a constant. So we have several constants with different arities, then they will be different, and we just roll with this. So maybe we don't actually need to declare things. But declaration helps us figure out which is defined and which isn't. You could just say that whatever is on the left-hand side is defined and the rest are instance relations. I think the name extensional relation exists somewhere in the datalog literature. I'm not very familiar. So datalog is very much like prolog, except that it doesn't have any function symbols. So the only thing that you have is variable, constants, and relations. So maybe we'll go on. We'll say a rule. A rule is made of a head, the head is something. The head is an atom, so I need an atom first. Yeah. Type atom. Has a root, which is a declaration. And it has arguments, which is a list of arg. That's not how you spell list in Ocaml. And I didn't define arg yet. Okay, I'm not going to call that an atom, I'm going to call that a literal. So an argument is either a var var or an atom of atom. And we're going to say that atoms are strings too. I don't know what they used to be, but it doesn't really matter. So I'll do this. We'll see. Maybe implicit. That's literal. Now we want rules. The head is literal. And the tail. Let me do something. Why does it indent 4? I don't like this. Oh, because it's... Oh, I see. That makes sense. It's twice 2. That's... I am a witness. These are literally 2 things for some reason. Not tail. Right-hand side is a list of literals. Oops. But no, I'm allowed to do this, aren't I? I'm not. Bound constructor list. Tell me about this. Oh, I see. There are some. I see. There were some leftovers from the from the emojis from earlier. That's a rule. A goal is just we'll be a bit lazy on this. Type program. So we need instance. It's a list of declarations. Rules is a list of rules. And the goal is a goal. Achievement. We're going to define the semantics for this. But I mean, you get the idea. Now we're going to do something similar for the relational algebra. I'm going to do that in a separate module that I should move eventually. Module rel algebra equals struct and We're going to reuse the declaration type from earlier, I guess. So these are common. I'm feeling a bit dizzy, sorry. So in relational algebra, we are completely and fully point free. At this point, we don't have a notion of variable, but we might find ways to emulate them. We'll figure it out as we go. I haven't thought about it enough, to be honest. I know it's possible, so I didn't really think about it too much. So I think we're going to say that there's going to be some trickery there, but anyway. Yeah, I feel that I'm missing something to make it really simple, but that's going to be fine. Okay. So we will similarly have a bunch of declarations, which are so a relational program is a collection of instance relation declaration of name and arrays in the future. There can be bounds which significantly there will be bounds, I think. We'll find a way to give it bounds. E.g. given by atom types significantly fascinating. Reduce the size of the generated set problem. Definitions of relations and binders. So we need relation expressions and constraints. Which for now will just be a conjunctive formula, I guess. Okay. A constraint, we'll say. On a constraint, which for simplicity we will assume is a single relation. Assume for now a single relation, and the constraint is that it is non-empty. So here we will have, oh yeah, I guess, does it want to, yeah, okay. Type expression. So an expression will be one of these things that we can define about relation. Kind of makes you want to put the arity of the relation in their type, but so that would be an intersection of two relations. So I need to be able to name variable of declaration. So we can of course make a check, but we'll just fail catastrophically when we generate something wrong. Union, we'll need that of expression, start expression. Yeah, I think we'll do the we'll say Cartesian product, like we'll call it cross of expression and expression. Not necessarily the same arity, and we want to do we want to be able to say that two columns are equal, I guess, two values, a relation is a predicate on a tuple, and we're going to say, well, we're going to filter out these tuples where value like the component number n and the component number p are the same. So and we also need a projection of int atom. Now we're filtering out these where this atom, and we say we're going to remove the second column. I'm not sure that's quite what we want. Maybe we just want to project, like we'll want to shuffle these things. So I'm not exactly sure what the best way to do this is. I feel that there's probably just a small way to do this very locally that I haven't figured yet. We're not going to do it this way. So there will be some, okay, there will be some reshuffling to do. I'm not going to call that proj. I'm going to call that filter. I think there's usually a name. I don't remember what it is. I'm going to call it, no, there's already a same. I'm just going to call it each atom. That is fair enough. There are some things missing. I have to think about it. I'll get back there. So for now, like a formula is going to be sum of x per. The relation is not empty. Right. Cod also defines all, it's full and lone, that it has at most one element and things like this. And you can also take conjunctions, and there's some stuff going on. I'll figure it out. So now we want to define a program. And we have instance, which is declaration list. It's more important in this one, I guess. We have, so we can define binding. We have like it's a not really like this terminology. Yes, that's the name of our variable, and that would be the declaration, and the body. Well, we can call it right hand side as earlier is an expression. So here we have bindings. They're ordered, so you can define a binding using another binding, I guess, like a previous binding, but they're not recursive. And that's just a binding list. And finally, you have a constraint, and that is just a formula. That's just a keyword is all. Okay. I think I need to change the Dune thing to talk about this file. No, I just need to name, right, I need to talk about it in main so that it compiles. So let's go to main.ml and do open datalog. I'm not sure it builds. So to check that, it's very easy. You add a syntax error and you see what happens. You tell me syntax error in datalog.ml. Ain't that grand? Boom. We have managed to define a thing. Okay. So the general idea is we want to, one, compile a rule to an expression, to define a relation in like define a binding for all the rules for the same all the rules for the same relation by taking the union of the compilation of these rules. I may need some atomic things there, like true and false. True is a bit worrisome. It's a bit harder to manipulate than false. In the game plan anyway, like following the code paper. There is some trickery in code to do this sort of things. Okay. I'm just thinking that I'd like the a visualization mechanism for all this to just appear by magic, because I don't want to do it. Eventually. So what's the idea here? So let's ignore recursion for now. Recursion is very, very important. That's the goal of everything. But let's assume that our prolog is not allowed to be recursive. So I don't have to deal with recursion. So I can if the datalog is not recursive, then I'm generating a valid program. So now I just want to define the function compile rule. It takes a rule, returns rel algebra. You know what? We're going to rename this to rel alg for now. Dot expression. That's the point. Equals an R. Okay. So I don't quite know what we want to do right now. So, like, we have a rule like this. So the typical form. Sure. A rule looks like this. R of x, y equals S of y colon T of x a, for instance, where a is an atom. So one thing that the code paper does that I'm gonna switch. I hope, David, you're still here to tell me to switch back after that. So in code, there's a tool that might be useful for this. You define maybe I'll be able to. There's this thing that generalizes over all of the things that we might. That maybe generalizes over all these equals and sigmas, etc. So you generate a new variable v that is locally bound That's a relation that contains a single element. Sort of, it says, that's pretty much what it says. So the semantic of this expression is you take the semantics of the formula together with v bound to x. Yeah, it's not entirely clear, but like here x is a set, like it's a set of tuples, so x here shouldn't have the thingies, because it's not a one-uple. Maybe it has to be. Maybe that's the idea. I don't think so. It's supposed to be just a set. But I was wondering if I could use this to transpose the variables more directly. Maybe that's an intent. They don't like define the type of binding, do they? Do they? There's some vars, some identifiers. Yeah, I don't really know. Like if that's a single variable and that is not a relation, then I don't really know how you can use it. And there's no example of this. But I think it works at any arity based on what's... That's a vardicle. Vardicle and expr, yeah, sure. Which is not the same as a rel, I guess. I don't know what this is supposed to mean. Aside from that, hey, I thought about switching on my own. Aside from that, I'm not entirely sure what is the easiest way to convince oneself that we shuffled everything properly. If I'm capable of generating a singleton relation like this, can I use it, and with what primitives? Like if I have, like, suppose I have t, not t, I'm going to call it like x, which is a relation containing a singleton relation. XY. Let's do can I define SY, that's a conjunction, TXA. Can I define SY? I'm not sure. That is not entirely clear. Something missing here. There's no doubt that there's ways to define a translation of rules to relation expressions like this. for now, we can assume as well that we only have variables in the rule. This is very easy then to add some constraints. So, can I? I guess it's just a matter of saying, oh, I'm going to take the Cartesian product of the two, then I take the equality of the column blanc with the column blue, and then I project on the columns that were already there. So it exists. And if I get the singleton thing, I know its arity. Can I write a function that makes it easy? Got to think of arity blah, and I want to apply it to variable flu, and right. So I kind of need a mapping of variables to columns in that one relation. So maybe I can spare the relation altogether. Either. Yeah, having this will just let me do the reshuffle much easier because I just do sum of something, like I say. Yeah. This is just I can use this just as a relation as a formula saying, oh, I need this to exist for the x and the y, and I take the union of all these. Let me have a quick look for a second on how it's compiled. I think I'm possibly getting somewhere with this. I'm giving myself a bit of a richer thing than usual translators, but it's okay. Just I don't really want to do too much. Too much column management. It might not be too hard. I don't know. I think it's probably pretty slow. It has to traverse all possible tuples. Not actually sure what that means. Maybe we just want to do this column management. I'm not sure exactly what it should be. Then we can do something like this. We can define so that this is a bit worrisome because that includes top. So we could define as top xy, sy, txa, and define this as sort of we do the Cartesian product of all this. We apply the filters that are given by this. These corresponds to column of this or to this, and then we just project on the first two columns. I think that's sort of the easiest way to do this. I'm not too happy to introduce top early on, but I don't see a good way without it right now. And that means it's going to be just as slow as the other rule, actually. But it doesn't make of expert. Oh no, of top of int. Int is the arity in case we need it. So in the rule, we can define the arity of a rule. Rule arity. That's really the arity of the head of the rule, but you know, rule to int equals for now, and we're going to do r dot head dot. That's original. Oh no, it's okay. It's a literal. Head is a literal and want its root. What was the rest? Dot Unix. Oh, I see. We can complete with any module. That's root dot arity. Here. Thanks, completion. Now we can say let n equal rule arity of r int. Oh, it's unused. Oh my god. So what we're going to do is we're going to take the Cartesian product of everything in the rule. So we are going to, I don't know, let free RHS equals cross of top n of, sorry, regalg.top n. Actually, yeah, let's cross of top n and of fold L of, I don't know what type that should be, and what type that should be. Oh yeah, that's not how you spell it in Ocaml. And that's fold left. That is supposed to be the list. So that will be my rule.rhs. What? Oh, r.rhs, sorry. That's a list of literals. So I assume this is to be yes, this is to be top n. No top 0 really. Doesn't add anything. And this is, thank you for giving me a full rundown. Syntax error. Oh yeah. Remember this. It's fun that it hasn't been solved yet. A to B to A, so that's accumulator first. So that's you know, a relation. I can just call it acc. B is my element, so that's a literal, and that would be cross of ac and l dot root. This expression has that declaration, but expression. Oh yeah, okay. Oops. Type expr. Oh yeah, I need to do var of this. Now at the end, we can return. We have ways to iterate on integers. Maybe containers give us the way. Let's have a look at containers. PubCount, eh? That's convenient. Oh. Infix operators. I assume not. Everything is there. Maybe the lib has one of these. Nope. There's no Ocaml expert in chat. That would have been very useful, you know. So what are we going to do with this? We are going to... we need to project. I don't even know how to project yet. I'm not... Oh. Right, so we need to be able to select a subset of the columns. We could just take a list of the indices and project on these. What's the semantics of it? It means, what's the semantics of it, of this projection? Well, it means if there exists anything in the rest. It's a bit of a disjunction. So is it better to remove? I think we could do that in one pass, because that's going to be way easier. I mean, just more efficient because we're going to do tons of passes otherwise. Yes, we could also do NRE cross products. Doesn't really matter either way. Going to do proj of int list expr, and all indices in range. Oops. So, oops, I call it prof as well. So basically, this corresponds to select in you know, our friendly friend SQL. Same together with cross product. We'll implement joins and ecatum. Well, there's just a condition. We kind of need all of these in SQL. So now that we have this, we can generate, I think, where am I? I still didn't switch, but that's okay. Okay, so okay, you missed a bit. I just added this there. I really hate to forget this thing. I don't exactly know how I forget to. It's kind of curious. If we go back to CC list, I think there are generators of lists that, or maybe I need to make an iterator. I don't know, like offsec or. Full map, full flat map, count through, init. Oh, that's good. So we can do this. So we're gonna do zero counting. Oh, again, I forgot. No, I didn't forget this time. My brain is not working. It's all fine. We're here to have fun. I hear that some people enjoy seeing me suffer. That doesn't really count as suffering. Yeah. But it's kind of. So I can do proj. Well, I'll do proj. And our first argument will be cclist.init, or int will be our arity n, and the filtered bit will be just so annoying. But when we're done with this, we've done like 80% of the work that is needed. For this step, I'll do the next step. I think next time, so that's in 2 weeks, we'll focus on implementing the relational algebra to SAT transformation. I will have to remember how to use MSAT, which is always fun because it's a bit of a it's a great library, but it's hard to find your way through it, I'd say. And that would just be fun, I to I. I still have the other function. Right, that's the one. So that will create the list 0, 1 for the binary case. And what? And filtered RHS. So now it's really about filling this particular hole. Yeah, well, it may bring us to the end of this stream. So now we have a bunch of columns on both sides. And for each of the rules, we want to equalize some columns. Right now, I just assume that everything is a variable in the head. So I'm not going to consider the fact. I'm going to just error out if there is a thing. So we need to collect the variables and map them to an arity, to a position. which is just their position in the list. So we can just make a function let pos of a variable. What did you say that variables were? Ooh. Variable, not these variables here, they're type var. Okay, so there's just a name, so of a variable v, we could call it x rather, that sounds more like a variable, and so that's cc list dot find maybe, right? No, that doesn't give me the index. Maybe there's index. Indices, mappy. There's things like index of. How do I navigate through my, not like this? I don't actually know how I navigate through them. With this, let me just left. I want to know the position of a thing in a list. Is that hard? Because if I look at find, it takes a bool and return an element of this thing. Okay. Mem returns a boolean if an element exists. That's kind of not. That's kind of not very nice. I mean, it's mem sort, remove a sort, split, combine, sort, fast sort. Oh. Well, okay then. There are some times where I miss the comprehensive library of articles. Just let index. So I will take article. Gonna call it index of. I will just take an A. I assume that the equality is easy. No, probably not. I'm going to take an A to bool just to avoid having to decide on the equality. A list of A returns the first index where there's one of these. And so equal fun PL code action. Code action. Oh, that's because it can't display list. Okay. Then the empty, it will just return asset false for the time being. Who cares? xl if p of x, then 0 else 1 plus, that's disgusting, 1 plus index of pl. What about that? One of the best Ocaml features, the rect keyword. So here we're going to do the same. We're going to do index of x, sorry. Of fun y. Well, we can just do equals apply to x. And here, the list that's r.head dot arguments, and they don't really have the right type, so equals var x. That's not the right type, is it? Yeah, maybe. Type arg. Right, that works. So we just assume there's no atom. So have a bunch of to-dos here. To-dos. Handle the case where there are atoms in the head of the wheel. That really doesn't affect the pos thing too much. Handle recursion. Will do eventually. Okay, so pos is not used yet, but we're going to use it a lot in filtered RHS. Because what we want to do, we want to get a bunch of equalities. So we want to define filters. Do I want to define filters? Do I have a scan? There's a scan. That is good. So, oops. So we can pair up every one of the let offsetted. So here I'm going to take the rule right hand side. That's the list of literal, and for each of these, I'm going to just do list.map. And I'm going to function, and I'm going to write in at the end. And the function, I'm going to do list.scan first. I'm going to need a few lists. Maybe guess these are the offsets. So let's call this offsets. Here's a scan. So we need an original accumulator, and that would be n. So we count the starting position of each of these things. So n will be the starting position of the of this first rule, etc., etc. And then we get fun p, fun o for the offset, and a literal, and we do o plus l dot root dot arity. So these are my offsets. Right, it's CC list. Scan left. Now let's offset it. It is just it's just a zip, but we have one too many elements. So do I need to drop it? That would be combine. Combine shortest. CC list dot combine shortest offsets and what? And l dot RHS. Okay, so now we have all of our right hand sides, and for each of these we're going to add filters, which is going to be a sort of two for loops in the shape of folds. So pre-RHS is our initial value. List.fullLeft. So there will be a function here. And what did we say? The initial value is the one before last. We fold over the RHS again. And here we say, here we're going to need several lines, so let's give us a few lines. So that's our block, and yeah. Here's we're going to say begin, end. So we have an accumulator, which is the value, the current expression. How can it not be wrong? I wonder how I will be able to debug this thing. We'll have to give ourselves good visualization tools. Hopefully the asset false will help. So we have a literal, and for each of the arguments we want to do a filter. So we start doing another full left. Here we have the accumulator and L dot arguments. Here rewrite fun inner arg case arg. Let's write arg there's okay. I wonder if this will work. It did. So we've got a var x, then the answer is regalg dot filter or dot same plus x. Oh, I need aha. Oh right, it's not argument that I want. It's not RHS that I want, because I have offsetted there, so I want offsetted. That's the whole point. Could do that in one step, but and so here I want an offset and an L. Here though, I just need full left I, which I think exists. I just need to figure out what the type is. I can just write it here and I will show it. It will happen. Sorry. I need to look for it. Full left I. No, it doesn't exist. Interesting. There's iteri, there's... Really? It doesn't exist? Why not? I mean, I can define it. It's just so annoying. This fold I is like fold, but I don't know which direction fold is. Okay. Why is there a fold? I'm so fully confused. You're not seeing what I'm seeing right now, but whatever. I don't want to forget to. I'm not sure there's actually a fold. Fold product, fold flat map. There's a lot of weird fold functions. No, there's no fold. It's still recursive, so I assume... Yeah, I assume fold I is full left. Okay. I think we can assume this. Oh. And then the int argument is here. So same plus x and off plus I. And inner. Oh, and it doesn't actually, oh, I didn't know that. That's an actual hole. Atom A, we say relalg dot eq atom. That's off plus I, a inner. So I'm gonna change the order of these two things for symmetry. And that's it, actually. That was easier than I thought. Just took me 2 hours, easy. Like a bit less than 2 hours, an hour, I guess. So there's a bit of a what do we do next sort of thing. What does that mean? Oh, there's a code action to do, I see. That's funny. Okay, so I think this actually compiles a rule that doesn't have recursion. So it assumes that whenever it sees a name, it compiles it to the same name, and it just assumes that the result is well formed. What we're going to do, I guess, when we get to make a full program is we're going to define well formed as a function that we will run on the output of the compilation, just in case there is something wrong and it says it there rather than arbitrarily somewhere. I'm not sure, maybe the asset failures will be enough. So to recapitulate, like we first transform it to top cross S cross T then apply same Ocaml corresponding to the variable atom arguments of S and T finally, we project on the first two columns. So we have done neither of these things. How do we deal with atoms in the head of the rule? I don't know yet. We have to add back the atom somehow. Probably not very hard. Might require well, I guess we have to be careful about. I'm going to call this top 2. It might be that it's either we actually add like top 2 as well, but we filter. We add a filter for this, like a unique atom. But there's a bit complicated. Well, maybe it's the best though. So I guess I want to do a group by now. So browser, is there a group by here? Some kind of grouping thing? Yay! There are joins as well. That's cool. Seymour actually added quite a lot of useful functions. Pretty neat. Yes. So I like the type of this because T is list, as you can see. And so here there's alpha list T, just for sort of uniformity, I guess, with all the modules. Hey, what do I know? So, yes, let's go back without forgetting to switch. Hey, to do this, and we're going to do let compile rules. It takes a list of rules and returns we'll return a list of bindings. I'm going to use the Haskell convention here. So first we want to group is that the only grouping function? Group join by. Group sucks. Okay, we have to be a bit careful here. So we want to do group by of we want to specify the hash, we want to specify the equality. And besides this, we want grouped equals to rs in. Okay. Interesting. Oh, because that's okay. CC list. So my goal is to group things by their root declaration. So it really doesn't know. Hash. Oops. Isn't there a hash in Ocaml? But there's there's one in CC, the CC hash, isn't there? CC hash. But CC hash is not generic and like really can't be bothered. Okay. So thought there was a generic hash function in Ocaml. Hash tables. Hash table.hash. Okay. Yay. Okay. So that's hash table.hash. Not too happy though. Why is this a to int? Oh, okay. That means I need a function from har, and I want to hash r.head dot root. I'm just quickly looking if there's an equivalent to the on function. No. It's fine. R1, it wouldn't have worked anyway. Well, it might have. No, that's eq. That's r.head.root equals r.head. R2 head.root. Well, that's a bit gross. Oops. Interestingly, can't infer the type. So now we have a bunch of lists of the same head. And now it's just a simple map, I guess. We can do list on map, begin end on grouped. So now we have each group is a bunch of does that work? Okay, maybe that's a good layout. Each group is it's bad. Oh, interesting. We'll see. Each group is all the definitions of the same declaration. The first thing we want to return a binding, and a binding is so. Can I do? I think I just need one actually. So relalg dot var equals headies dot. It's very confused. Root dot head. Okay. This is RHS equals, and that's where we're going to have to think. That's head like this. Root dot just root. Oh, maybe just root. Oh, that should be a literal. I'm confused. These is a rule. Oh, that's because it's not root. It's head dot root. And bound value head, of course. So my right hand side has an unknown type, of course, too. So what is this right hand side? This right hand side is the result of a fold and a map. Should I? Oh, I'm not in there. Should I use full map? Yeah. So what do we want to do? We want for each of the declaration to compile it, and then we just want to fold the union. So I think we're going to do list.fullLeft of fun R1, R2 union R1, R2. We need a bottom. We know that the list D's is non-empty. Would be nice if I had a non-empty full left. So what we can do is we can do the initial value is head D's and tail D's here. That just avoids using this dot tail and list dot head. Okay, this what is saying that. Okay, so that's not quite D's that I want to do. First, let compiled equal, and here I can just replace D's by compiled. In, and here I want to do list the map. List the map, and I want to just compile rule D's. Wow, look at this. We actually have a compiler now. Let's check that. We can build. That's exactly what we expect. That is good. What do I want to do with this? We also kind of want to compile the goal, and then we can get actually I said right now the goal is a conjunction, but I think we actually want existentials. They're not really hard to define, but we can just define the variables as meaning existentials. For now, we just said it was grounded. It was ground, sorry, not grounded. Dear Lord. So I said goal, ground conjunction, was it existentially defined conjunction. Oh, literals. But we can just assume that we don't care. So it's just So how do we compile a goal? So you have a collection of things. They also correspond to an expression. Compile goal takes a list of literals, returns an expression. Let's assume first that to-dos handle existentially quantified variables in goal. I think it's almost sleepy time. So, I'll explain something before I leave. I think I should have done that earlier. Compile goal, literal list, tralalg, exper, r. Here we're going to compile each of these independently. Taking the conjunction. I think we want to build the cross product again. So we have something a bit similar like this. So we don't really have an arity there yet. And we don't have the top here. I'm not sure I'm handling there are some further conditions, like you're usually saying datalog if there's a variable in the left hand side, it's necessarily defined in the right hand side, and that gives you better translations, but we can revisit them later. That's free const, I guess, and that is just the goal. I don't know why I call it R here. So now we laid all of them. So right now I'm going to mostly ignore this and just, so we're going to do the offsets thing again, and we're going to ignore the var case for now. So we're going to compute the offsets and offset it that way. Yeah, I guess it is very similar to the other one. We kind of want the top, current ID, handle the existentially quantified variable like the defined relation for rules. That is, add the top relation of the arity, number of existentially quantified variables. And use similar stuff. So I'm going to prepare for that then. Oops, no, I can't. I need to here. No. Oh yes, shit. Okay. Let's just kill this. What? So here I'm going to use 0 as the arity. Pre-constraint. And here is G. Here is G. Here's G. And now we're going to do something. So can we factor the initial bit with compilable? We're going to do something very similar here. I'm just copying everything. That's pre-conster, offsetted. So here I'm going to say false. And here right. So here we're just adding all of these to the Cartesian product. Well, yeah, actually that's sort of the same thing. And at the end, we use the Cartesian product to means end, but not really in the same line. So at the end, we just return filtered RHS. Right. Then it was projected. So we're going to do something. We're going to return a formula rather than an expr. And it's going to be more symmetric. Here, that's filtered. Filtered conster. And here, we're just going to return some There we go. Okay, so I wanted to show a little something. Let's just check the builds. Okay, so I'm going to stop programming here. So let's fold this into this, and now push to master, whatever. Spin-off branch. Oops. Database. Datalog. Yes, spin-off for real this time, and we're going to call this datalog, whatever. And we're going to push this. So what am I getting with this? It's something that I sort of forgot to include. So we have an example logic here. So here we have ranges, and I don't care about that. I'm going to talk about the rules. In the rules, we have, if I can reach this, I can reach this if I have the bow, and I have eastern key, and I can this and that, etc., etc. All fine. However, that gets a bit more interesting. We don't define reach and have, and we don't, and there's a hidden assignment variable there. So there's somewhere an assign that says, I'm going to take an item and I'm going to put it in a location. There are rules on this saying I can't add two items to the same location. I can't add the same item to two locations. I can define these two rules as goals, I think. I might need a bit an extended logic, but that's not going to be a particularly big problem. I'm just saying, all these things are not legal. There's exactly one item per location, etc. I'm not entirely sure I'm gonna manage to do this. There's some trickery involved, but I think that works. And so you would just define, so my instance definition here, what am I here? My instance definition to say, I've got this assign relation that I decide to define, and it has, like right now, everything has arities that are integers. In the future, we probably want the arities to have types that will significantly reduce the size of the problem, but for a number of reasons. But there it is. And therefore, as well, we have this thing that if I can reach a location and there's an item X, so we have a location L. If I can reach L and there's an item X in L, so X is assigned to L, then I have X. And that's how we can read these out. So you might notice that there are no variables here. That's because that was kind of the goal. And it is not necessarily important to have a variable. These are atoms. Instead, we can have rules. But anyway, these are atoms, and I can mention them, but I need to take care of the case where atoms are heads. The general idea. So we'll have we can add, like right now we have a single goal, but I can phrase it as having a goal and a bunch of constraint conditions. So it can be existentially quantified, and possibly allowed to have negations in the goal. it can be a fairly extensive formula. The goal it's right now is very simple, but we can make it something more complex. I can like there's not a lot of difference between a constraint on an instance and the goal, so I can just add this as the same thing. So the general idea that going here is that instead of having all this logic built in about what it means for something to be somewhere, you can have many of these. There can be some stuff for keys if they're different. You can have other things randomized and have different relations between things. Like if you want to do a door randomizer, you can define exit blah goes to there. You can define as a formula. The exits are coupled. That means if I go to a place, I go to another place. But the relation goes to is symmetric, basically, between two exits. These things can be added. And the key to that is that relational semantics is actually quite easy. Relational things are quite easy to compile as SAT problems. It is not very different from what I had done before. Before I had said, oh, all these rules, I'm going to duplicate them, and I count the number of steps that we do, except we can do something a bit more principled, because we can really count, based on the number of atoms, the number of times we need to iterate. Which might be bigger than this, but it's kind of fine. And it's going to be, here I'm sure I'm making assumptions that are not actually completely true, and don't necessarily generalize to several relations. Here I'm just defining reach. Well, I'm defining have as well, but it's not mutually recursive. And then you can do a lot of things to reduce the number of recursions that you have to do. One of them is to compute your connected components, so that you have a sort of order in which you compute things, and then you have fewer things that compute at the same time. You can use the types to limit the number of things as well, the number of things that if you have types on your relations, they have fewer maximum number of elements, which is going to be key. So that's sort of the general idea. That was supposed to be a slow day to get back in shape. Something went really wrong at the beginning. I guess that was funny at the very least. I kind of need to go back to this at some point. Sorry, not to go back, but to clean some things up, like get my Ocaml working and get this browser problem fixed. I didn't really have a work plan for this. I don't know where to start. So I'm rambling a bit. But here is I should have maybe started with this, but this will, I think this will make this randomizer engine much more general, and it's a good thing. And it's still a proof of concept. It's not going to be very polished unless someone says, oh, I really need you to polish this, in which case, but it's going to say more things. I don't really know how I want to treat these ranges. So these are just variables, and you can sort of, like, they have natural interpretation in the relational logic, so you could easily do that. And these are constraints, or maybe, I don't know exactly how we want to represent that, if we want to have a more general, if we may keep the same syntax. I don't know. There's plenty of things to discover, and we're going to discover them as we go. We have, I haven't shown it again, but we have a compiler that produces ZDD that we will be able to use to compare and debug I don't intend to remove the ZDD at all, even when we have a better generation, because it's exact, which is good, and it's also good for debugging, at least on small instances, because on big instances it's going to be too slow. So yeah, it so happens that in the past few months I read sufficiently many things that I couldn't really wait until I was like I really wanted to revisit this project and to do a couple of things with it, and I'm kind of excited. I hadn't done any Ocaml for probably a year or more, but that's fun too. Yes. So there's no conclusion to this train of thought. I'm going to stop it with no conclusion then. So, my point in all this is to say goodbye, thank you for listening or watching or catching up in the VOD. This is for fun, this is for sharing. Come share, say things, share ideas, complain, joke, all these things. So we're going to be at this for a few months probably, because I always do these things like every other weeks, and there are holidays coming, and I'm going to miss some weeks as always. Next week we're going to get back to solving some randomizer things, though the Christmas special from last year was quite special indeed, which has very different kinds of logic. We're going to make a few extra dungeons. Hopefully I'm not going to die for an hour on the same boss. And 2 weeks from now, we are going to come back to this, and probably we're going to start by making a relational algebra to Boolean stuff compiler. Like, I know this compiler is not complete, but it gives me the first skeleton, so I'm going to do the other part, and then we can sort of chain them, and it's going to be fun. One of the thing that was hard before was this idea of grounding. So handling variables was hard, and that's why I designed something that had no variables. But that means that there are all these implicit relations. I thought I was saying goodbye, but I'm not saying goodbye anymore. Hey. Sorry. Yeah, I'm, and I think that it was a bit problematic, and it just itched me the wrong way. But doing a full grounder sounded very difficult. But that being said, Code just tells you, no, grounding is easy, so go for it. Basically, well, it doesn't really do grounding. It does just represents things in a certain way that just implicitly grounds everything, just by using a restricted language where it just works. Basically, I was just saying basically in the tone basically. So it's really time to say goodnight for tonight. So yeah, again, thank you. I hope you had fun. I had fun, though I'm sure I'm going to have more fun next time, because starting was a bit hard, and I was, as I said in the beginning, a bit unprepared, and that's entirely my fault. There's all the things I'm preparing and I'm working on, and that's sort of what's been keeping me. That being said, again, next time Zelda, and then we're coming back to this, and then, once every other week. I've been talking for way too long, and that has no point. I'm going to say goodbye now. Goodbye, good night, or not good night, depending on the time it is where you are. And until next time, don't forget to stay curious.